Hello dear students, in this part we will discuss concept of vapor pressure and Rawls law. See, this particular lesson will be very important for this chapter because the coming further topics of this chapter are entirely based on concept of vapor pressure and Rawls law. So let's start. Okay, in order to understand the concept of vapor pressure, we need to first understand the evaporation process. So what is evaporation process? See, we take a container in which there is some liquid and we analyze the bulk molecule of this liquid. This bulk molecule will be surrounded by many other molecules from all the possible direction, and hence net force acting over it will be zero. But if you consider the surface molecule has unbalanced force over it. There will be molecules below it, but there would be some above forces lacking over it. That's why a net upward direction force will be acting in this, and that allows this molecule to come out in form of vapor spontaneously. Hence, the spontaneous conversion of liquid molecules present at the surface into vapor is evaporation. And see, this evaporation take place at any particular temperature. So either it is 10 degrees Celsius, 100 degrees Celsius, any temperature below its boiling point, evaporation can be possible. So if you consider an open container only, then that there will be only evaporation. So why we are discussing this? Very soon we will find out that. Rate of evaporation is directly proportional to temperature, because if you increase temperature, you are actually providing more energy to the molecule to come out of it. If there is more surface area, then there will be more evaporation, because higher the surface area, higher the surface sites and higher the surface molecule. If there is more force of attraction between the liquid molecule, then it will not allow the molecule to go out. Hence, the evaporation will become less. Okay. Now let's consider a closed container. So in a closed container, the surface molecule will be showing evaporation, but these molecules after colliding with top surface will start condensing also. So both evaporation and condensation will be taking place in a closed container. How? Let's see. At t is equal to 0, there will be only evaporation with maximum rate. But when the time passes at t some time greater than 0, evaporation will be taking place with its own constant rate, but there will be condensation also, and this rate of condensation will be increasing. There will come a time at which rate of condensation and evaporation will become equal. There will be a dynamic equilibrium between these two, and at this dynamic equilibrium we can plot this graph. See, y-axis as rate, x-axis as time. So as time increases, the evaporation rate is almost constant, but see, the condensation rate is increasing slowly, and there comes a time which we name as T equilibrium, where evaporation and condensation rate becomes equal. So at this equilibrium stage, the pressure exerted by vapors formed in the condition of dynamic equilibrium over the liquid surface is called vapor pressure. So finally we can say that vapor pressure is the pressure exerted by vapor molecule at the vapor liquid interface at the state of dynamic equilibrium in a closed container. Okay, now let's understand this concept of vapor pressure through this chemical equation. Suppose we have water liquid and it is getting converted to water vapor, and the state of dynamic equilibrium, we are writing equilibrium constant Kp. So this is the pressure of product, that is P of S2O divided by concentration of reactant. Since the reactant is pure solvent, hence its concentration value will be 1. So finally the vapor pressure, that is PS2O, will be equal to equilibrium constant. See, now in case of H2O, the vapor pressure is also known as aqueous tension. It is very important common term which is most widely used in our chemistry. Now, as the vapor pressure is equal to equilibrium constant, and we know that equilibrium constant is only function of temperature, hence we can say that the vapor pressure will be function of temperature only. So with increase in temperature, the vapor pressure increases. It is directly proportional to vapor pressure, because this particular conversion is endothermic, and through Le Chatelier principle, if we increase the temperature, the reaction will shift forward. Now we can draw this graph. With increase in temperature, pressure is increasing. Now if we see the intermolecular forces between the particle, then it will be inversely proportional to intermolecular forces, because the higher the intermolecular forces, lower will be its chance to go out and convert into vapor. Now this point is very important. Vapor pressure is independent of amount of solution, surface area, volume, shape, size of container. So in finally we can conclude that vapor pressure actually depend only on temperature and intermolecular forces. Apart from that, vapor pressure do not depend upon any shape, size of container, amount of container, volume, surface area or any other thing. So many questions are asked based on this concept only. Okay, now let's consider the vapor pressure of solution, and in that we'll consider a solute, and we can have two type of solute. Either the solute will be volatile or it will be non-volatile. So if it is volatile, then it will definitely have some vapor pressure. Its vapor pressure will not be zero. But in case of volatile, its vapor pressure will be equal to, in case of non-volatile, its vapor pressure will be equal to zero. So volatile component example can be camphor, petrol, etc. And you can have any ionic solid as non-volatile component. Also we have to consider that size of the solute is always greater than size of solvent in this particular chapter discussion. See, this important result has to be understood very well. It is said that pressure of solution is less than pressure of vapor pressure of pure solvent, and that solution is containing the non-volatile solute. So when we add non-volatile solute to any pure solvent, actually its vapor pressure decreases because it blocks some of the surface sites and restrict the passage of solvent molecule into vapor. So it blocks the surface site and it will not be converted into vapor. Also it is blocking the path of solvent molecule. So finally the vapor pressure in solution decreases if non-volatile solute is added to it. Now we will discuss very important law, that is Raoult's law. First of all, Raoult's law is valid only for volatile component only. So in case of non-volatile, your vapor pressure becomes zero. So in that case, Raoult's law is not applicable. So volatile component, vapor pressure of volatile component in any solution will be directly proportional to mole fraction of that component in liquid state. So this is Raoult's law. So Raoult's law actually states that in any mixture of containing some volatile components, if you need to write the vapor pressure of some ith component, it will be directly proportional to mole fraction of that component. So if you remove this proportionality, you will get proportionality constant, and this proportionality constant is pure component vapor pressure. That is Pi is equal to Pi naught into Xi. Suppose you have a container and we have mixed some A or B into it, two different component, and Xc and Xb are mole fraction in liquid solution. So it will, according to this Raoult's law, this pressure of A will be equal to Pa naught Xa, and pressure of B can be written as Pb naught Xb. Pa will definitely be less than Pa naught because Xa will be less than 1, and through this mathematical equation we can say that Pa is less than Pa naught. Okay, now according to Dalton's law, the total pressure can be written as sum of individual component pressure. So P total will, or P solution is equal to Pa plus Pb. Pa can be written as Pa naught Xa and Pb can be written as Pb naught Xb. So total pressure or pressure of solution can be written as Pa naught Xa plus Pb naught Xb. Now based on that, we will discuss the graphical representation of this Raoult's law. So see, here a graph is drawn which has two different origin. First one is X is equal to 0, Xb is equal to 1. So this states the point where only B is present. And when we move from left to right, the B amount is decreasing, X amount is increasing. So at this point only A is present, X is equal to 1, Xb equal to 0. Now according to Raoult's law, we have Pa is equal to Pa naught Xa and Pb is equal to Pb naught Xb. So Pa is equal to Pa naught Xa is this particular line, and Pb is equal to Pb naught Xb is this particular line. Now combining these two, we will get total pressure, that is Pa naught Xa plus Pb naught Xb, and we can write Xb as 1 minus Xa. So rearranging, we get this equation, and we can plot this equation and we will get this particular path. So in this graph, this particular path is total pressure. Total pressure is Pb naught, Pa naught minus Pb naught into Xa. Just put the Xa value is equal to 0, you will get Pb naught, and see at Xa is equal to, you are getting Pb naught is equal to 0. So I hope this graph is understood by you. Or here we have taken an assumption that Pa naught is greater than Pb naught, that is you can say that A is more volatile than B. Okay. Now we will try to find out the vapor phase composition. See, in this particular diagram, Xa and Xb are mole fraction of A and B in liquid solution. But if you see, the component will also be present in vapor, and its vapor pressure or its vapor phase composition is represented in terms of Ya and Yb. So Xa, Xb are liquid phase mole fraction, and Ya, Yb are you can say vapor phase mole fraction. Now according to Dalton's law, you can say that partial pressure is equal to mole fraction into total pressure. So Pa can be written as Ya into P total, Pb can be written as Yb into P total, because Ya and Yb are vapor phase mole fraction. Now Raoult's law will state that Pa as Xa Pa naught and Pb as Xb Pb naught. We just studied this particular part. Now at equilibrium, these two Pa values will be equal. So we can write Pa is equal to Ya P total is equal to Xa Pa naught. From here we can find xi is equal to this particular expression. Similarly, xb is equal to this particular expression, and we can write that xa plus xb must be equal to 1. So putting the values over here, we can rearrange to get this particular equation, that is 1 by p total is equal to ya by pa naught plus yb by pb naught. So rearranging this, we can also get this particular equation, which can be helpful in drawing this particular graph. In last case, means in case of your this liquid phase composition, we have drawn a graph which was pressure versus mole fraction. Now in this case, we are drawing a graph which is 1 by pressure versus mole fraction in vapor phase, and this is this type of straight line which can be verified through this equation. You just, in this equation, you just put ya is equal to 0. If you put y is equal to 0, 1 by p total is equal to 1 by pb naught. So y is equal to 0 is here, and it is 1 by pb naught. So it is verified. Okay. Now let's solve some important question based on the concept which we have studied right now, and we will understand the concept more easily. First question states that there is 1 mole of heptane whose vapor pressure is given, is mixed with 4 mole of octane whose vapor pressure is also given, and forms ideal solution. We have to find vapor pressure of solution. So first ideal solution is that solution which follows Rawls law. So if you have to find vapor pressure of solution, then you need to have individual vapor pressure of heptane and octane. So pure component vapor pressure are given and moles are given. So in order to find the individual vapor pressure, we need to have mole fraction. So let's find mole fraction of heptane, that is mole of heptane upon total mole is 1 by 5, and subtracting it from 1 we get mole fraction of octane, that is 4 by 5. Now total pressure of solution is pressure of heptane plus pressure of octane, that can be find out with the help of Rawls law. Now putting the values over here, we can get the final result as 43.2 mm of Hg as total pressure of solution. So this was plain and simple application of Rawls law. Let's solve another question which will clear our concept of vapor phase composition. So in this question, we have to find composition of vapor phase which is in equilibrium with benzene toluene solution with liquid phase mole fraction as 0.4 for benzene. Now pure component vapor pressure are given for benzene and toluene. So see, x of benzene, that is liquid phase mole fraction of benzene, is 0.4. So after subtracting it from 1, we get liquid phase mole fraction of toluene, that is 0.6. So using Rawls law, you can find total pressure. So putting the values, we get the total pressure at 69.8 torr. Actually, we have to find YB and YT, that is vapor phase mole fraction. So we know that the pressure can be equated from Rawls law and Dalton's law. So this is Dalton's law and this is Rawls law. We can equate this two to get YB, and XB is known, PB naught is known, P total we just calculated over here. So finally YB, that is mole fraction of benzene in vapor phase, is 0.681. Subtracting this particular value from 1, we get mole fraction of toluene, that is 0.319. So see, liquid phase mole fraction was 0.4 and 0.6. However, vapor phase mole fraction is 0.681 and 0.319. We can see that vapor phase mole fraction of benzene is more because benzene is more volatile over here, as its pure component vapor phase pressure is high. I hope you would have understand the concept, and we have solved the question based on this concept very easily. All the best for preparation. Thank you. Thanks for watching. Please like, share and subscribe for further updates.